I'll do that. Thank you very much, Dr. Niessen.
Okay. Well, good morning, everybody. And I say good morning also to those who are not online yet, but I will not do it later. You may have noticed by looking at the program that today and tomorrow we actually have, together with the discussion of the exercise, only 3 sessions instead of the 4 we had on the previous 2 days. And there's something weird with this course, because this in principle is a 2-day course, and we spread it out over 5 sessions. And the reason for that is that I basically need to have 4 exercise moments, so 4 homework exercise moments in the online setting, and that's why we have 5 days. So we will not probably not work until 12 until 1 o'clock today, and I know you don't mind. And also tomorrow we will stop a little bit earlier. But then I've already told you this. I don't know if I told you that in the beginning of the course, but this is something which we have. So I hope to see somewhat more faces, because I have only 6 of the participants now with their cameras on. And well, fortunately, some others are joining us right now. Great. So let's discuss the exercises. How was your general feeling on the exercises? Was it tough? Was it easy? Was it doable? Or you can also just somebody to start on the first one.
Come on, you got extra points for start talking right now.
I can start.
It's gonna be
Yeah, that would be nice.
Extra points, my friend.
Yeah, that went easier than others. So
Okay. Yeah, I think that's a general. If you start talking for the first exercise, these are always easier than the other ones. So, okay.
maybe okay.
Give it a try.
Yeah. So as we saw, it was given to us the A and B ring Z values, and it was given that R1, 2, and 3 are hydrogen, and that's very easy to see if you just draw the structure. I used Chem Sketch and I drew structure, and then I put hydrogens, and of course I got 240, the neutral mass. Then I tried to separate work on A ring and on B ring. So I drew A ring as we got, and then just try to fit there the smaller adduct OH, not adduct, but the smaller how do you call it, fragment or part. OH, and then I got 153, so I knew it's there. Then actually, as I continued working, I just kept changing A ring, and of course it was easy to see that 153 is OH, so it was substance 1, 2, and 4, and then for substance 3, I just put instead of OH, OCH3, and then the mass value was okay. I got 167. Then I went for the B ring, and knowing that adduction of hydrogen and hydrogen is 105. So when I add the hydrogen and OH group on either radical R2 or R3, then you get 121. So it's H and OH. And that is good for substance 1 and for substance 3, yes. And then, of course, we have 135. And this is can be achieved by adding OCH3. And then the B ring, how do we get 151? Instead of H, we put OH, and then we have an entire table filled in. So yeah, so that was quite straightforward, especially when using this ChemSketch free software. That's it.
Yeah. Okay. So when I actually built this exercise, I had a slightly different approach in solving the exercise. You come to the same conclusion, and because this is what you gave us, and that's basically what we see. But in general, I would say, so we have the 2 for 1, and we know about what is the 2 for 1 because that's basically given in the exercise. So what we see for the compound number 1 is a M over Z shift of 32. And since we can only have addition of oxygen or addition of methoxy, the 32 difference must be 2 oxygens. And we see that one of the oxygens is in the A fragment because we have a plus 16 here. And we have a plus 16 here. So the other oxygen must be in the B fragment. Yeah. And if we then proceed, and I basically proceed starting out from the compound number 1, and then we have the 287 for 2 and 3, indicating that we must have, instead of 2 oxygens, we must have an oxygen and a methoxy. And from the fact that the 153 fragment, the A fragment, is still the same, and we see the plus 14 in the B fragment, we conclude that we must have the methoxy on the B fragment. And with compound number 3, it's the other way around. So that's the way I would do it without making any drawings or something like that, just from the information which is in the setup. But you come to the same conclusion, and there's no reason for abandoning using the software drawing structures, because that's what I do a lot myself as well in interpreting spectra. So thank you, Maxim. Any questions on this? If not, let's move to the next one, the spiritin. Can I have a volunteer for this one?
Yeah, I will try.
Okay.
Okay, so the molecule is very similar to the molecule in the previous question. So if you break it in the middle of the molecule between the 2 oxygens, you get from 303 the 153.
Yeah, so you do the retro deals all the fragmentation.
Yeah.
Like this, yeah, okay.
And okay, and after that we can see that the gaps between the 303 and 285 and 267 is loss of 18. So I guess it's loss of a molecule of water, of OH2. So,
yeah. So we have water loss here and another water loss to the 267. Yeah, I agree.
Yeah, and well, and this is where I stop. This is where I stuck a bit.
So I have a question to you, but also to all the others. You said if we do the retro deals Alder, we get 153.
Yes.
And the 153 is the this side of the molecule. And I always I have learned that we cannot talk about the left side and the right side, but it's at least the left side of the structure. My question would be, quite often we see not only the 13A, but also the 13B. Do we see a 13B in this case?
It's the 151 next to 149.
Exactly, that's the 151. Yeah, because we know the two fragments, the 13A and the 13B, should add up to m plus h plus 1. So if we have the 153, we can calculate the other one must be the 151, and the 151 is there. So that's the 13B. That means that we have basically 3 more ions to go. And one of this is the 275, which of course is, instead of the loss of water, a loss of CO from the m plus h. I see Anna agreeing with me. That's good. And now we only have 2 ions left, which is the 177 and the 149. Does anybody have ideas about that?
I was thinking that maybe it's a breakage of bond 1,4 and right side of the molecule. Yes.
Yeah. So we cut like this and we keep the charge at this side. Yeah. That's the 177. Yeah. And then I would say, if you have the 177 and you have it like this, you can easily understand that you can have a CO loss from that. So you lose 28 from the 177 and you get the 149. Which means that basically what we see is the 2 retrodiazolyl fragments. And we get the 14B due to the 1,4 cleavage, followed by the loss of CO from that to the 149.
Yeah, I got 149 differently. I got it by cutting the OH groups, the ones on the left and on the bottom.
These two?
Yes, and the cutting the breaking CC bond, the head of this molecule. And also breaking the O, the lactone, or how to call it, the oxy maybe.
Yeah, I don't immediately see how you come to 149 then.
How can I share my screen?
Yeah, possibly.
No, but maybe you must allow me.
I don't know. I don't know if
Then
you can try. If you can share your screen.
It says because you're sharing.
Okay, I will pause my sharing. Perhaps now you can.
Let's try.
If not, I will stop sharing.
To try, it's okay.
I just opened the options, so try again.
Oh yeah. Okay. Do you want to continue? Yes. Here. That one. Now you see, that is how I got 149. Is it? Can you see it?
Yeah, and the most important point which I have against this,
yes,
is actually this line. This line.
That
because
one?
what you do is you cut the carbon-carbon between 2 rings, and this is something which we
not happens
almost never see.
So it's very rare.
It's very rare. Yes, it's very rare. In fact, I have only one clear example where I am sure that we have such a carbon-carbon cleavage between the 2 rings, and that's one of the examples which we see today, later on today.
Okay, so I stop sharing now.
Yeah. Okay. Yeah. Great. Thank you. So we are back, and I have to make sure that I can still see you all, and also my own data. Let me see what's going on. Oh no, I do something completely wrong. Okay. Yeah. So
I have a question about 149. You depicted it as a triple bond between C and C, yes, and plus H. And what is better to, how to better to present it, or double bond, CH and plus on it, on carbon?
I actually don't have a clear answer to this. I have, in general, some preference of writing fragments as a protonated molecule, but of course, there's no solid proof that it's a protonated molecule or not. If you would like to have the double bond, I would expect that the charge will sitting on the alpha carbon.
I mean, how is it better to present in the papers, for example?
I don't know.
Okay.
I simply don't know. There's no obvious way of doing this. If I would say, if I would have a look at my structure proposal for the 13A, I basically wrote it as a protonated molecule, also to have the butadiene, so the diene feature in, which you would expect from the retrodiesaldr. Yeah, because basically that I can't show it on that, but basically what you will get in the retrodiesaldr is you get a diene and a substituted ethylene from how the retrodiesaldr works. But it's always extremely difficult to say, hey, I should write a structure like this. And the way I deal with this is say, what I do is I give structure proposals. And then somebody can say, no, it should look like this, or it should look like that. It's fine with me. I don't, quite often don't know where exactly the charge will sit. And that's part of the discussion we had before on where's the charge in a protonated molecule anyway.
Could you please share the screen?
Oh, sorry. Let me see how I do this. Because
Green button on the low side over there. The green button says share screen.
yeah, but I don't see the button. I don't see the.
Maybe it's up there if it's not.
I'm completely lost in how it used to look. Right. I'm completely lost in the screen. I only see you, God.
And when you press share screen, the window opens.
I don't have a bar, the bar which usually allowed me to.
Okay,
look.
try.
So probably I will go out and get back in again. Would that be?
You can try move your mouse to the top of the screen. Maybe it's in the top of your screen. It'll just fall down. Then
No, it doesn't.
Share screen.
Doesn't. I will leave and then come. Oh,
Okay.
wait. Okay. Yes. So now I have to do it like this, and I share screen. I take this one, share screen, and then go back to. Okay, now I'm back to what I have. I use all these programs so much that sometimes I get lost in. What we
Still
do.
don't see
You
the
see
share
black.
screen is coming up. Yeah, just it's sometimes it gets stuck for a minute or two. It's okay.
You see the sharing now?
No, it's
Still
red
not.
screen.
It's very odd.
It's very odd. So probably I will leave the meeting and come back.
Okay.
That might
We're
be
here.
the easiest way to do so.
Back in track, and we can see a screen. Thank you very much.
That's I would say a standard procedure with your first try when you have a computer program, and that is reboot. Well, I didn't reboot, but get out and get back in. That would be the same as rebooting the complete computer. Okay, I'm happy that I'm back and I can still see you. We have solved a important computer program. So let's move on to exercise number 3. And there we have 2 spectra. So we can have somebody for the first one and we can have somebody for the second, or we have some just one for all of them. Who I can give the word?
I can go.
Yes, please.
Okay, so for the first one, 220 is the cleavage of the OC bond to the, yes, with the,
This one?
yeah, exactly. And then 202 is on the other side of the oxygen, yeah. And 174 is next to the carbonyl from the other side, yeah.
Yeah.
Yes.
Okay.
And
Okay.
the 91 is the tropylium ion?
Yeah.
Okay.
Yeah. Okay. So if you cleave at this side, you see the loss of C2H4. So you have hydrogen rearrangement to the oxygen. Then you see the loss of water, or you see the loss of ethanol from the M+H. And we see the loss of CO from the 2O2 because the carboxylic acid function is sitting on an aliphatic carbon. I also have to point out that, yes, I think the 91 is the C7H7, but it's not completely clear to me how it is formed. Because in principle, if you would form it directly from the M+H, you will have to cut 2 carbon bonds from the same carbon. Actually, you have to cut 3 carbon bonds from the same carbon and also have to rearrange some hydrogens to the ion. So it's a bit weird what is going on here. And since we don't have any in-between ions, it's because basically you would like to see how, for instance, the nitrogen ring will fall apart. We cannot say any conclusive things about that, but well, the 91 will be the C7H7 plus. Okay, so if there are no further questions, we can move to anisodamin. Do you take that as well, Shirley?
No problem. Okay, so the 288 is the loss of water, and 276 is, I think, the loss of the nitrogen and the methyl on the top.
Which means that you assume that the 276 is an auto-electron ion.
Okay.
Because if you take out the nitrogen,
Mm-hmm.
the mass of the compound will be even.
Mm-hmm.
And also you take out you take out a radical, which I don't think is very likely. I actually have an easier explanation for the 276 being the loss of the formaldehyde from here.
Ah, okay.
And do you have any idea where the water loss comes from? Is it from the tropic acid or from the from this side?
I would say from the ring, just by intuition.
This one? From this one?
Yeah, I thought.
Yeah, I agree.
Okay.
I agree. Okay.
And then 140 is from the oxygen to the ring on the top. It's
Yeah.
cleavage. Yeah.
And if you do this, what you lose is the tropic acid. So if you write the resulting fragment as a protonated molecule, you will put a double bond in the ring. Yeah?
Mm-hmm.
Okay.
And then 122 is the cleavage of the CC bond on the bottom next to the ester bond.
Which one?
Below
Yes.
the carbonyl? Below the carbonyl? Yes.
And you keep the charge at the bottom?
I think so.
Which again would be a radical,
Ah, okay.
because this bloody nitrogen rule.
It's not
Perhaps-
just the
The
loss
loss
of
of
water
water.
from the upper part.
Sorry?
Yes.
It's not just a loss of
water.
water from the upper part, because we
The
already
loss of water from the upper part would be more likely,
Okay.
especially because earlier you convinced me that this 288 is due to the water loss from this group. And if you cut the bonds to produce the 140, the OH is still in there. So the 122 is the loss of water from the 140. And if you would write the resulting fragment as a protonated molecule, that means that you put an additional double bond in the ring. Yeah?
Mhm.
And then we move to the 91.
So I also thought this was the tropylium ion, but I don't know.
Yes, it's a tropylium ion, but actually it's the tropylium ion from the top part of the molecule, because what we see is from the 122, we get secondary fragmentation involving the loss of methylamine. So now we lose the nitrogen. And in losing the methylamine, we put an additional double bond in the ring. That means that we now have a 7-membered ring with 1, 2, 3 double bonds and a positive charge. And that's the 91. Yeah. And perhaps you have considered the idea that the 91 could come from the topic acid. In fact, I know that this 91 can come from the top part of the molecule, because I've also seen spectra of some of the metabolites of anisodamine. And one of the metabolites is the hydrolysis product, this. So you have a dehydroxytropine, which shows loss of water, loss of water, loss of 31. So again, it's producing the 91, which is a good indication that the 91 can actually be formed from the 6-hydroxytropine. Yeah. Thank you for this. So I have the scheme, which is which I'm showing here right now for the fragmentation. That's what we said. And I'd like to point out that basically we have now seen 3 different spectra from esters, where we see some typical features. So in the mepiridine or betidine spectrum, we see the loss of CO at a certain stage because it's on the aliphatic ring. Where in our previous example for the para-hydroxybenzoic acid butyl ester, we actually saw the loss of CO2 from the acid because it's sitting on an aromatic ring. And both in this case and in the case of the mepiridine, we see the loss of the group attached to the ester, and we don't see the fragments where the charge resides at that side, because both the ethyl group and the butyl group have much lower proton affinity than the other part. While in the anisodamine, the proton affinity of the tertiary nitrogen is much higher than that of the lower part. So in fact, now by cleaving in the ester, we keep the charge at the top. And these are the fragments which we see. So we see the 3 different situations which were outlined by the fragmentation scheme of the protonated ester in this particular case. And in all these cases, we do not have the complementary ions, because either the charge goes at one side or the charge goes to another side. And of course, there are examples where you see both. Okay. So let's move to exercise number 4. Anyone interested in talking us through, or at least starting to do?
I can try.
Please.
Okay. I suppose that we have a cleavage between C and O, and we have a fragment with 3 for 3, and one more in position between O and C. It gives us a fragment with mass 3, 5, 9.
Yeah, and what are the bonds which you cleave? Because you say between C and O, but there are many C and O.
Yes. The first one, I mean that we lost a fragment OCCO CH3. Actually.
So you assume that you cut at this point?
Yes.
Yes?
No. After O. Between
Here.
S in this position. Yes. This.
Exactly. So if you lose this group,
yes,
you get 3 for 3.
Yes. And
if you would do it on the other side?
In the other side, I give a fragment 3, 5, 10, 9.
Exactly.
Okay.
Yeah?
Yes.
Okay.
And
so let me please allow me. So
Mhm.
basically what you do is in cleaving either this group off or the isopropanol off, you are creating acylium ions with
Yes.
either the charge on that side or the charge on that side.
Yes.
Okay. So then we go to the 301.
Okay. And okay. And 419, it's just a molecular ion plus H. 301, it's I think it's plus OH group in position one of on the sides after cleavage. I think.
I think what you mean is
yes.
If we
Yes,
take
yes.
the 343 and we see the loss of the propene.
Yes.
So we
And
cut this carbon oxygen bond, have hydrogen rearrangement to the oxygen.
Yes, and
Yeah.
and
that's 343.
Okay.
Sorry, that's just a 301 then. Yeah, because we lose 42 from the 343.
Yes, exactly.
And in the same way, we can also say we start out with the 359, and we now cut at this side of the oxygen. So we cut at this side of the oxygen, and we also get 301.
Yes, exactly.
Yeah, and that means that if we do it from the 359, we have done a charge remote fragmentation because the charge is here, and you lose a group from this side. And if we do it from the 343, you again have a charge remote fragmentation because the charge is sitting here, and you lose. Yeah, that's
yes, exactly.
And what we now have is if we
it doesn't matter, but
no, if we have a look at the 301, we have at one side a acylium ion or oxonium ion, and at the other side we have the carboxylic acid function. Yeah.
Yes.
Okay.
The mass 200 83, I think it's just a loss of water.
Yeah. And where does the water loss come from?
I suppose because we have OH group and H and H with nitrogen, maybe this is the water. I think.
But I don't think the nitrogen will give away its hydrogen that easily. So we have a complication there, and I'm happy that you are aware of the fact that we have a complication, because quite often people say, well, we see loss of water, and of course, yes, it's the loss of water. But in order to get a complete story, also adhering to the fragmentation rules I've put out, I need to give you a small scheme. And the scheme will, of course, be in the handout, which will be sent to you later on, because you don't have to draw it now. Yeah? It will be in the handout. So I start out with my 419. I do the cleavage of the COO binding on either side, and we can have the 359 and the 343. And then we do the charge remote fragmentation, losing the other parts. And basically what I did is I started out from this one to have this one, but if you do it the other way around, it's the same in 301. And then I say, now I will see the loss of water, and the easiest way to explain what is going on is basically shake up the ring. So I aromatize the ring, which means that I now write it as a protonated molecule. I have an acid at the one side and an aldehyde at the other side. And from this structure, I can readily explain the loss of water. And then we also see the 255, which perhaps you would say it's a loss of CO. Exactly. But if it would be the loss of CO, it will not be this CO.
Yes, of course.
Because we just learned that that doesn't happen. It must come from the aldehyde.
Okay.
Yeah?
Yes.
However, if I go to the accurate mass data, which you don't have, but I have, I can see that the elemental composition of this ion leads to a M/Z value which is not observed. We actually see another 255. And well, we see a 255, which is an odd electron ion due to the loss of the NO2 dot. Yeah. So we don't see this CO loss. We see the loss of NO2 dot from the 301. And that is what accurate mass tells us. But my important point, of course, this is something which you can't know. My important point is, of course, in this part of the story where you take off parts and then at a certain stage you come to a structure where you see I must lose water, but how to do. And this is a way to propose how the water loss can easily be done. And some other people said, well, we can also take a hydrogen from the methyl and get a ring here, but well, these are different ways of describing the ion. Yeah.
Yes, but and with the last masses mass I had problem. I did identified it.
Yeah, I have serious problems there as well, and the only way I can explain the 89 would be this structure. So cutting this bond, but I don't believe that this is something which is happening. Unfortunately, the ion M/Z 98, which I found in a particular spectrum, which was the basis for what I show, didn't show up in the accurate mass data. So I don't have a confirmation that this is correct. And I actually hardly can believe that this is something which can occur. So it might be some artifact which was in the original data, or I don't know. Yeah. And well, these things happen. Sometimes you see ions which you cannot immediately explain. Okay. Unless there are further questions on this one. Let's move on to exercise number 5, which is a drug MET-ID approach. And you may be aware of the fact that the approach we follow here is actually completely the same as the approach we used in the first exercise for the retro-Diels-Alder fragments. So we look at the shift in the M+H and try to pinpoint this shift to the product ions.
Maybe I would like to try.
Yeah, please.
So I'm not sure about the M1, so I will leave it in the end. But the M2, I suppose that to the fragment 200.
Before you proceed, if we say we have a -14, what would you expect to have for a -14?
So CH3.
Yeah, you have demethylation.
Yeah, this is what I thought.
And you should be aware of the fact that, of course, if you have demethylation, you effectively lose CH2, eh?
Okay, yes.
Because
yes,
you cannot take off a methyl from a molecule, then you have to have the hydrogen instead.
Yeah,
And
so I thought that probably there's a CH2, but I wasn't sure. Okay, great.
Can you tell where the CH2 loss occurs?
Yes, it goes from the fragment 130.
So it must be an demethylation.
Yes, here.
Yeah?
Yes, yes.
Because the 250 is the same.
Yeah, exactly.
The -14 we have here, so we must have an N-demethylation.
Yeah.
Yeah.
Yes.
Okay. So you were not sure about the M1, so now we are.
Yes, great.
Okay.
So M2, there is the addition of the substituent OH to the fragment 215.
Yeah.
And then the same.
So the hydroxylation must be somewhere down here.
Yeah, or could it be? Or could
so it would be either on the ring or on this side.
I thought on the carbon, where is the cleavage next to it? Could it be? Or no?
I already have 4 bonds, so that would be a bit difficult.
Yeah,
then
sure.
You get a problem with your organic chemist.
Yeah, no. I know that's the carbon only 4.
Oh.
Okay.
Sorry, but why not to add methox instead of methyl? It will be the same.
Sorry?
Instead of methyl to the part of 215, I mean, we can do options to add oxygen or to add hydroxy group on aromatic ring, or we can, instead of methyl, to put methoxy group on carbon.
So what you say is what I have is I have demethylation here?
No. I'm telling that M1, M2 can be either, where is +16, it can be either addition of OH, as it was mentioned, on aromatic ring, but why not to, instead of CH3, to put methoxy group?
Because metabolic enzymes don't do that.
Excuse me?
Metabolic enzymes don't do that. So there are no enzymes in your body which will replace the methyl group by a methoxy.
Okay.
As simple as that. So we can't do that. And maybe there are in plants there are enzymes like that, but in the human body it doesn't occur, because this is basically an MOVZ shift which is not in the tables I showed you before.
Okay.
Yeah. Okay.
So the M3 again the OH, but this time to the fragment of 130. So it will be the binding between oxygen and H. So that's like a this formation of the group.
And I think what we can say from the +16 here and the 146 is that the +16 must be somewhere in this part of the molecule, and we don't know where.
Okay. Okay.
Yeah, so
Mm.
it can be actually we can say we have basically two possibilities. It can be on one of the carbons, or it can be an N oxide.
Okay.
But it will be in this part of the molecule, but we cannot say about position because we don't have fragments to prove where it is going. We can only say it must be there.
Okay.
Yeah.
So the M4, it's addition of OCH3 because it's
No, because OCH3 would be 30 and we see 32.
Okay. So this I don't know then.
Maybe O2.
Exactly. Exactly. So what we see is a deoxidation.
Okay.
And since we have a +16 relative to the M3, the two oxygens will actually sit on the 130 fragment. So in this part of the molecule. Whereas in M4, where we also have a +32,
So
the two oxygens will sit on the other part of the molecule because we have the 32 to the 250.
Yes.
So what we basically have, we have N demethylation. We have hydroxy on the phenyl or on the methyl group there. We have an OH or an N oxide in the end part of the molecule. And we have either two in that part or two oxidations on that part. And since we don't see any further fragmentation, we cannot make any further statements on positions where they are, at least not from the evidence which we have. Okay. So let's move to number 6. Which perhaps was a bit interesting or tough. Did you come up with some ideas?
I can try, maybe with mistakes.
That doesn't matter. That's not not getting the right answer is part of the learning process, I would say. So please.
Okay, so I started from the second part, just calculating what was the difference between non-substituted molecule and the new molecule. Okay.
Yeah.
I just made calculation of elemental composition and differences in elemental composition.
Yeah, from what we have here, yes?
Yes, I started from this part.
Yeah,
Great.
okay.
And after this, I go to the upper part to show the differences. And I think that number 2 will be methylation on nitrogen.
And methylation, yeah, exactly.
Number 3, we adding fluorine F, which is 19. So we have somewhere F on aromatic ring because 91 was affected. I mean, everything that to the left was affected. So it's sitting somewhere on aromatic ring.
Yeah. So we have a fluorine on the aromatic ring and you say fluorine is 19, but of course you are replacing a hydrogen.
Yes, sure.
So the effect is you have a plus 18. Okay. That's number 3.
Yes. Number 4, we have 2 modifications. So the same F on aromatic ring, and additionally we have methylation on nitrogen.
I agree on that. So we say we have
difference of CH. Yes.
Yeah. Yeah. Exactly.
N and F. So by differences, I decided that two parts of molecule were affected.
Yeah. Yeah. And you are aware of the fact that we are now doing something completely different from what we did in the previous exercise, because in the previous exercise we were looking at endogenous metabolites, so metabolites of a certain compound in the body by the enzymes. This is synthesis. Yeah. So we can do things which you cannot do, you cannot get in the metabolism. For instance, you never get the addition of a fluorine in a metabolic reaction. But here we can, because we do synthesis. Yeah. Okay. Let's move to number 5.
No, yes, number 5. I have a methoxy group on CH2, and
which you have a methoxy group on this position?
Yes.
Why?
Let me make a calculation. 1 moment. I need to remind. We have.
I would. My question would basically be, why would it sit here and not on the ring?
It can be.
Yeah, it can be.
And
in fact, I would expect that if you have it sitting on the alpha carbon, it might actually influence this fragmentation here.
Okay.
So I would actually expect that it's sitting on the ring.
Okay. And number 6, I have 1 moment, where it is. I have final structure of it was formate on carbon, which is close to aromatic ring, and from another side, methylation on nitrogen. I mean, 2 additions.
Yeah, again, okay. The methylation of the nitrogen comes immediately from the +14 difference, which we see between the fragment number 1 and the shift.
Yeah.
And in fact, the structure is a bit different, because the structure what you get for this one is this, and it is very difficult to actually show that this is what is there, because the fragmentation is not completely conclusive about that. But this would be one of the possibilities of getting the CO2 in to the molecule. And in fact, of course, the spectra were spectra taken from a library of these specific structures. So I'm sure about the structure.
But my question is to have 135 minus 105, it will be 30. So it can be loss of CH2O, yes? So it theoretically can be formula on the carbon. Yes?
Yeah, but then you need to have an additional oxygen somewhere. And if you and that's one of the things I did. I also and these things will be all these pages will be in the handout, where you basically explain some of the peaks which are there from the accurate mass. So we know the elemental composition, and in that we can actually more or less confirm the structures which we have. So this is what you came up with, except for the last one, but I don't mind. So these are the structure proposals which come to it, and also indicating the position of the fluorine. Although we cannot, I can tell you that if you would have the 2 or the 4 fluorine, you will basically get the same spectra. So you cannot readily discriminate between these. I've explained some of the other fragments which are there, and in going through, you will be able to see some of the features which are there. Yeah. So I think you did a marvelous job, all of you so far, from explaining what is there, and there's always some small issues which you have to you will not be certain of, and but it's there. Okay. So let's move to the last one then. Is there somebody who would like to do this one? If not,
it's also synthetic molecules. It's not something that.
No, this is metabolism.
Metabolism. So once more,
metabolism.
Issue of enzyme activity.
Yeah. So I will talk you through. Yeah, that's probably easiest because I don't have immediate volunteer. So for the first one, we see a plus 32, which indicates that we must have 2 oxygens. And then we try to find out where the 2 oxygens are. And the first thing which we notice is that we have a plus 16 in the 465. That means that at this side of the molecule, we only have 1 oxygen, telling us that we must have 1 oxygen in the C group. And now we have to try to find out where the other oxygen is. Yeah, and in principle, we can already conclude that from the 380, because the 380 is a fragment more or less related to this 465, or basically cleaving at the other side of the nitrogen, but charged at this side. And the 380 is due to the loss of this group from the 480. And we see that now we have lost the oxygen. So the other oxygen, we said there must be 1 in C. The other oxygen must be in the A. And that is basically confirmed by the fact that if we just lose this group and produce the 513, we have lost 1 of the 2 oxygens. There's only 1 oxygen in the molecule left. And you see the same for the 421, but that doesn't really matter. You see the same for the 338. But we already concluded that 1 oxygen must be in the C part of the molecule. So C and A. Yeah. Metabolites, is that all clear? Metabolite number 2 and 3 are both due to hydrolysis. So in number 2, we see a shift of 132, and you would have a shift of 132 if you take off this part and replace it by hydrogen. So we have hydrolysis and loss of C. And in the same way, we can explain metabolite number 3, which is showing the loss of this group, so hydrolysis of this bond. And then the rest is not affected. And metabolite number 4 and number 5, they both give a plus 16, and they are actually completely the same. So these are 2 isomers with different positions of the oxidation. And since the 465 is the same, the oxidation must be in the C ring. So what we have is we have a double oxidation, 1 in the A and 1 in the C for number 1. We have losses of C group and D group for 2 and 3. And we have hydroxylation and 2 different positions in the C from for 4 and 5. Yeah, is that what you got?
I have some question. For example, oxygen and NH2 have the same masses? Is it possible that I just don't know if enzymes exist to exchange OH for NH3? In this case, B can be changed in any of the molecules because it doesn't change any molecular mass of part B.
You mean I could have changes here?
Exactly.
Yeah, but again, that is not something which is happening. So what you can have is you can have an amino function which is replaced by an OH. Yeah, but what you then see is you will see the mass going up 1 unit, and it must go up 1 unit because if you remove the nitrogen and put an oxygen instead, you are removing the nitrogen, so the you go from odd to even or even to odd. That's the nitrogen rule. But I am not aware of any enzymes in our body which can actually replace the OH by NH.
Okay.
Yeah. So the other way around goes easily, but that not. Okay. Being at the end of the exercises, and it's slightly over 11, so we have our break first before we proceed for the next session. So I see you in 10 minutes. Do some exercise. Okay, if anybody, we all are back, we can proceed. So switch on your camera so I can see that you're back. So hopefully the others will soon follow. I will start again. And in the two presentations I have for tomorrow, for this morning, we discuss about the fragmentation of nitrogen compounds. But as you may have seen, I sometimes put in additional things, also tools in order to think about fragmentation and how to sort out fragmentation and so on and so forth, and to proceed. And that I will continue with doing in this session as well. So if we start discussing about nitrogen fragmentation, we can get back to the amines, where we basically said we can have, we will see cleavages of carbon-nitrogen bonds leading to complementary ions, one involving charge retention, so the protonated amine and the loss of the alkene, and the charge migration leading to the protonated alkene or the alkyl cation and the loss of the amine, and the latter one you only see if you have sufficient proton affinity in the alkene part of the molecule. And if you see both ions, if you see both ions, they add up to the M/Z values add up to M plus H plus 1. And that's basically what we already said in the second session of our course last week. So let's take an example. And the example I take comes from an exercise which we've done before, which was the dibromo compound. The compound is called bromhexin. And what we are going to do is we are going to take the 375 as a precursor ion and fragment it. And this is the MSMS spectrum which you get at certain collision energy conditions. And basically we have a tertiary amine. So we can have cleavage at this side of the nitrogen. We can have cleavage at this side of the nitrogen, but we will not see cleavages of this, because if we would have cleavage like this, if we get hydrogen rearrangement to the nitrogen, we will see the loss of CH2, and that's not a normal molecule which you would expect to see losses of. So if we follow the blue line, we get either the ion at the bottom or the ion at the top, which will be the 262 and the 114. If we follow the red line, the product ion 83 is actually observed, it's present in the spectrum. But given the fact that we don't see the 293, I actually believe that the 83 ion is not due to the fragmentation of the intact molecule, but actually due to secondary fragmentation of the 114 involving the loss of methylamine. And if I would acquire the spectrum at lower M/Z values, I will actually see this 32 appearing as well. There are some other ions in the spectra. We'll come back to them tomorrow, and then we will look at it again. But for now, we have these secondary fragments and the 83, which is there. I promised you tables, so let's have tables. If you have primary aliphatic amines, you can see losses of ammonia. For anilines, so aromatic primary amines, you don't see ammonia losses quite often. More often, you actually see losses of HCN, which means that you go from a 6-membered ring to a 5-membered ring. For methylanilines, but I don't have many examples for that, sometimes the losses of methyl radicals are reported. And if we have secondary and tertiary amines, we have the fragmentation we just discussed. And in addition, we know that we can have the alpha-beta carbon-carbon bond cleavage producing the iminium ions. And we had an example of that in one of our exercises as well. And then I also have to point out that if you have diaryl amines, and of course there should be a hydrogen and an additional hydrogen to the nitrogen, and you have the protonated form, the cleavage of the nitrogen carbon bond to the aromatic ring is unlikely. And you basically only see it at high collision energy. And I always say, if you hit hard enough, you get everything broken. And the reason for not seeing that is because hydrogen rearrangement, which is turned out to be necessary, is important. And I last year I studied, or over a couple of years, but last year I finished it. I studied a data set of 100 tyrosine kinase inhibitors, in which there were 38 which actually have this diaryl amine as a part of their structure. And I saw only CN bond cleavages at high collision energy for 4 out of these 38 compounds. So this is not something which is occurring too often, and that we can immediately see. So we are in the complementary ions. So let's look at an example. And one of the things I always like is that if you follow this course, that at a certain stage, if you see a structure, you can basically start predicting what is the fragmentation you will see, what you will get. Yeah, and in this particular case, we actually have 3 pairs of complementary ions in the spectrum, because the 57 and the 261 is 318, the 74 and the 244 is 318, the 130 and the 188 added together is 318. And if I look at the structure and say, I would expect a cleavage here, perhaps with charge retention on either side. I would expect to have a cleavage of this nitrogen carbon bond or this nitrogen carbon bond. And in fact, if I do so, and here I have indicated this, and you can you write out structures for the various fragments, you can immediately see that this is what we have. We have these complementary ions due to the cleavages indicated. So this is something which we can do once more. And now I basically start out from the structure and say I have this phenotyrosine. I can have cleavages of the nitrogen carbon bond to the ring, to the phenotyrosine ring, and I can have charge retention on either side. I can have the alpha beta carbon carbon cleavage relative to the nitrogen to produce the iminium ion, which is stabilized by resonance. I can have the alpha beta carbon carbon cleavage relative to this nitrogen, because I also get a stable iminium ion. And in principle, I could also have cleavage of this with charge retention on either side. So based on this prediction, I basically start looking at the spectrum. So what I do myself is I basically draw the structure, I predict where fragmentation is, and then I simply look at the fragments and see whether they show up by taking off parts in the molecule in the structure. And I see the 2 complementary ions 141 and 243 adding up to 375 for the cleavage along the blue line, the nitrogen carbon bond. I see the 246, which is the cleavage of the alpha beta carbon. I see the 113, which is the cleavage of the other alpha beta carbon. And here I see something different, because, and I don't have a clear explanation for that, what is going on. I don't see the fragment where the charge resides at the left-hand side of the molecule. I only see an ion related to this, which actually is an odd electron ion. So I get a homolytic cleavage of this nitrogen carbon bond. And I was very surprised with that. And basically, I can say we have a variety of phenotyrosines having this structure element in them, and all of them show this odd electron ion. And I can't explain why it's there, but I see it all the time. I also have to point out to you to one other ion, which surprised me a lot. But again, having a lot of phenotyrosines, you see them, you see it for all of them. And that is the fragment 214. The fragment 214 can be considered to be secondary fragmentation of the 246 involving the loss of a sulfur atom. So we lose the sulfur atom and the ring closes again. And I would not expect to see losses of sulfur atoms from a ring, but accurate mass tells us I've lost the sulfur. And I do not only see that with this compound, but the whole variety of these compounds. And in our session of tomorrow, we will discuss a little bit more about sulfur fragmentation. And one of the messages I will give you there is that if you have sulfur in your molecule, you always have to be aware of unusual, weird fragmentation. And this is just one of the examples where we see these losses of atomic sulfur. And I guess the ring will close again because that's the easiest way to draw it. Okay, in principle, and the M/Z70 is already an example of that, you could have cleavages of the piperacine ring as well. And this is something which is studied on the next page, next 2 pages actually, in a little bit more detail, because we look at the fragmentation we get in piperidine and piperacine rings. And basically what we will see is if we take R1 being a hydrogen, we see losses of ammonia, we see losses of nitrogen and carbon like this, and we see a loss of a nitrogen and 2 carbons like this. The loss of ammonia has been demonstrated to be a 2-step fragmentation reaction, and of course it must be a 2-step because you have to cut 2 bonds. And the first step is actually a hydrogen rearrangement from the beta hydrogen to the nitrogen, followed by the inductive cleavage of the other nitrogen carbon bond. Yeah, and that it is the beta hydrogen is actually demonstrated by doing labeled substances. So we have a labeled substance where we have deuterium labeling on the beta carbon, and we initially have 4 of these labels, and the ion 249 for the unlabeled substance is involving the loss of ammonia. And you see that from the labeled substance, we actually lose one of the deuterium labels. There are only 3 left in the compound, indicating that one of the deuteriums from the beta carbon is taken by the nitrogen. Yeah, we see this ammonia loss both from the piperidine, from the piperacine, and also from this ring. And in fact, the other fragmentation which we see is different between the piperidine and these other 2. And that has all to do with this position. So in this particular case, we can readily put a charge on if we cut this bond. In the nitrogen says, I want to have a hydrogen attached. I will not accept a charge. And the same holds for the sp2 carbon, which we have here. So for the piperidine, if we have the cleavage like this, we actually see the loss of methylamine, and the proposal for the resulting structure is indicated here. And for the other cleavage, we actually see the loss of 45, so ethylamine. And if you say, I see the loss of ethylamine, perhaps you say, instead of having this, we could also have this. Can you prove that this is not happening? Well, in fact, and you say, I claim this is happening. Well, I would say, if I would have the cleavage like this, so I see the loss of dimethylamine, I have to cut 2 carbon-carbon bonds, which is unlikely. Whereas if I have the loss of the ethylamine, I will cut a nitrogen carbon bond and a carbon-carbon bond at a tertiary carbon, which is more likely to do. And again, we have data from labeled compounds where we have 13C labeling on the alpha carbon. And then if you have the 223, which is actually the cleavage like this, which I propose, then we see that from the 2 carbon labels which were originally there, there's still 1 left, indicating that you don't do the cleavage like this, but you actually do the cleavage like this. Because of the differences which are there between the sp3 carbon here and the nitrogen or the sp2 carbon here, for the piperazine, we actually do not see the loss of methylamine, but we see the loss of the imine. And also for the other fragmentation, we see the loss of imine. So we see losses of 31 and 45 here. We see loss of 29 and 43 here. And these are different features of these molecules. And an example of that is shown in the spectrum of the myanserin, where in fact we should see the losses of the imines because we have a piperazine, and in this particular case, an N-methyl piperazine ring. So the first loss will not be the loss of ammonia, but the loss of methylamine. And then we have a dimethylamine loss, and we have the imine, like, where is it? The 222, so this one. And we can have the loss of this group to the 208. So that's what we see. And there are many compounds where you have these type of, so the methyl piperazine or the piperazine itself as a substituent to a molecule. You can have the piperidine ring as a molecule, and also morpholine rings as substituents to various different groups. And typical fragmentation, which you see in these cases, is outlined here on this particular page, where you see, depending on what is the R1 group, you see specific fragmentations. And this is all outlined. And if you run into such a compound, it is wise to go back here and see if this is helpful for you. But I will not go over it in detail, because in principle, I would need to have a lot of examples to show what is going on, because there's a lot of information in this page. Okay. Having discussed about primary, secondary, tertiary amines, cyclic amines, we should also say a few words about quaternary ammonium compounds. And I took this particular example because it actually shows us all the features which are important in the fragmentation of quaternary ammonium compounds. So what we can see is, we can see losses of the C2 group. And this is something which can actually take place in 3 different ways. Of course, from what we have learned so far, we would expect that we have the cleavage of the nitrogen carbon bond with hydrogen rearrangement to the nitrogen, so the loss of C2H4 to the product ion 100. In fact, what we also see is the loss of C2H6, so it's actually taking a hydrogen from the ring, producing a double bond in the ring, so we still have a quaternary ammonium compound with an M/Z 98. And in between these two, we see another product ion, which is 99, due to the loss of the ethyl radical. And these ethyl radical losses, in competition with other losses, are typical for these type of compounds. And of course, if we look at the loss of the methyl group, we can lose it as methane, so CH4, having a double bond in the ring to the 112. We can see the loss of the methyl radical to the 113. But of course, we don't see the loss of the CH2 with hydrogen rearrangement to the nitrogen, because the CH2 is not a molecule which we can lose. In fact, the smallest loss which you can have from a molecule, apart from possibly an H dot or an H2 loss, is 15 Ca3. And you cannot see CH2 losses. Yeah. A nice example of the fragmentation of a quaternary ammonium compound is this compound called chlormequat, which is a herbicide which is used in rice culture. And basically, the three major fragments which we see are all due to cleavages of the nitrogen-carbon bond. We see two fragments, which is the fragment 63, three fragments. One is the 63, where we have this cleavage and we have charge migration. So we see the loss of 3-methylamine, which is the 63 ion. We see a cleavage involving the loss of chlorethane. So we basically have a hydrogen rearrangement to the, I must say, a hydrogen shift to the carbon, and we get the product ion 58. And we also see a homolytic cleavage of this with charge retention on this side. So we get the odd electron ion, so the molecular ion of 3-methylamine at M over the 59. This herbicide is, as I said, frequently used in rice culture. And we have in Europe, we have some rice culture in the southern part of France, in the Camargue, and in the area around Valencia in Spain. And according to EU regulations, if you do a residue analysis of chlormequat in rice, you have to use a stable isotope labeled internal standards. And there are basically two stable isotope labeled internal standards which are used for the analysis of chlormequat. One is the D9, you have the spectrum of the D9 here, and the other one is the D4 analog, where we have a deuterium labeling there. And in the MSMS spectrum of the D9, you actually see something interesting. And we, of course, still see the 63 ion, the 58 ion containing 8 hydrogens moves up to 66. The 59 ion having 9 hydrogens moves up to 68. And if you compare the spectra 66, 68 to the 58, 59, you can see that the relative abundance has been changed. So for the formation of the 58 is more likely to occur for the non-labeled substance, or for the labeled substance, the formation of the 59. So this one, the odd electron ion, is more likely. And this is what we call a heavy atom effect. And you see this type of relative abundance differences between labeled and non-labeled substances. And in this particular case, we can easily explain the heavy atom effect, because here we just have homolytic cleavage. But in order to form this ion, we have to, instead of shifting a hydrogen, we have to shift a deuterium, which is 2 times the mass. So it's getting more complicated. And then the homolytic cleavage actually gives a more abundant peak. I'd also like to say some words about heterocyclic aromatic compounds. And this is an example of that. This is called atrazine. And what you actually see is you see a whole variety of fragment ions. So basically, one of the things which may be of use is either opening up MS1 resolution to have the isotope peaks in, or what I do is I create separate spectra for the compound with M over Z 216 with a 35 chloride isotope in, and the M over Z 218 with a 37 chloride isotope in. Yeah, and that's what I've done here. And you can see is that what you get is you get a number of fragments, and some of the fragments have show a shift of 2 units, indicating the chlorine is still in, while some other fragments do not show this, so the chlorine must be out. And this is something which you way to do this to see, get some additional information about the various ions. Alternatively, and that works very nicely with the atrazine, you can use the ms to the power n, which you have in the ion trap, allowing you to do a stepwise fragmentation. And I actually explained all the peaks as being a stepwise fragmentation, and the various steps are indicated by the numbers here in the middle column. So basically what we first see is the loss of 42. So we see the loss of the propene. And please let me remind you that at an earlier stage, when we had this example for the dibutyl pentyl amine, I said what we see in most cases is the loss of the largest alkyl group going preferentially. And that's basically what we see in the spectrum, because we see the loss of the propene, but we do not see a fragment due to the loss of the ethene. Yeah, that's the second step in the procedure. So in most cases, the largest alkyl group comes off first. From this 174, we have 3 secondary fragments. The largest one is the 146, involving the loss of the C2H4. We can see the loss of HCl to the 138, and we can actually have the ring opening like this, or like that, where we see another 42 loss, but now with a different elemental composition, being CH2N2, like this, to the 132. And we can see secondary fragmentation of these ions as indicated in the table. And then what you can do is start doing structure proposals for the various fragments. And then at the low end of the spectrum, you run into some problems. And of course, these compounds will not look like this, but will be probably just a square. But I draw them like this, so it's easier for you to see where they come from. And quite often, when I show this to organic chemists, they say, no, this is not stable, that doesn't happen. And then I say, well, I have a compound with 2 carbons, 3 nitrogens, 2 hydrogens, and RDBE of 3. Give me an alternative structure which does not involve complete rebuilding of the molecule. And then they say, well, so you are probably right in what you draw. And you can, of course, say something different, and so on and so forth. So what we have for the atrazine is we have a symmetric triazine. And if you would have a asymmetric triazine, you can always start questioning what is actually going on in this molecule, what is actually the fragmentation which you see. And last year, when we had the lockdown on the corona, I bumped into a molecule where I actually can nicely study this feature, and that's the anti-epileptic drug lamotrigine. And lamotrigine gives you a complicated MSMS spectrum with lots and lots of peaks. And basically, I will only focus on some of the peaks here in the spectra. And the reason for doing that is that I want to try to find out what is actually going on in the fragmentation of this asymmetric triacene ring. And I could do this by taking advantage of the fact that this compound is frequently analyzed in quantitative analysis for therapeutic drug monitoring, and that they use 4 different labeled substances, where I have these labeled substances, but also the position of the labels is different between these various compounds. So in fact, I can, from the quantitative data and from the SRM transitions which are reported in literature, I can basically say for a number of these, for these labeled substances, I can see a number of fragment ions. And based on this, and based on the elemental composition of the various product ions, and there should be a dot here at the it should be plus dot here at 166, by the way, you can basically say, okay, let's take the lamotrigine, the various stable isotope labeled standards, and indicate the position of the labels, and then look at the various fragments and the shifts in the fragments with the labeled substances, and try to explain what is going on, what is the type of fragmentation which you get. So we basically look at what is the loss in terms of elements, what is the most likely way to do this, also taking into account the shift which we have. So we know we must have 3 labels left in this particular molecule. We have 3 labels left in this one, and so on and so forth. So in that way, carefully studying all these data which we have, you come up to this conclusion. And from this, you can actually say, now I can tell the story in a complete way and say, what I have is this. I have the ring, I number the various atoms, and based on the data which I've acquired here, I can actually indicate which atoms are actually there in the various fragments indicated in the spectrum. So this is again a way where we use labeled substances to try to elucidate structures of these molecules and to get hold of what is going on in the fragmentation of these asymmetric rings. And I can tell you, it took me quite some time to figure this all out. Okay. Two more molecules to go. The first is cotinine, which is a metabolite of nicotine. And in this particular case, we see something which I consider unusual because I hardly see it. I only have a few examples where I see that, and that is the cleavage of a carbon-carbon bond between 2 rings. And the reason, the most likely reason why this is going on is the high stability of the protonated pyridine. So we actually see the cleavage of the 2 bonds leading to 2 complementary fragments, which is the 80, the base peak in the spectrum, and the 98. And from the 98, we can see the losses of CO to product ion 70, which can be drawn in different ways. And also, we see some losses from there directly. So next to that, we see some minor fragments involving the loss of methylamine. And then, of course, I will close the ring, followed by loss of CO. Okay. In 2014, I had a heart attack. And I was in the hospital for a week or so. And after a few weeks later, they repaired my heart by a nice daughter operation. And in the 6 months after my repair, I had a lot of trouble because I have a lot of complaints with my health. And I hope you haven't been in contact with cardiologists for your health. But if you have been, you know that cardiologists have a large hobby, and that is prescribing medication. So in the first week after my heart attack, I actually had more medication than I had in the 51 years before that. Yeah. So each time when I came to the cardiologist and I said, I have this complaint and so on, he said, well, I will give you we'll try a new drug. And one day he said to me, well, now I would like to prescribe you Norfasc. And he gave me the prescription, and I went to the pharmacy shop. And at the pharmacy shop in the Netherlands, you don't get the original drug, you always get the generic alternative when it's available. So the lady behind the desk in the pharmacy shop said to me, of course, you will not get the Norfasc, but what I will give you is the generic alternative, which is called amlodipine. And then, without thinking for just 1 second, I immediately replied to the lady, oh, that's very nice, because the amlodipine gives us a very nice MSM aspect. And she was standing there looking, should I now give him some psychoactive drugs? Is he mad? Is he crazy? But let's face it, it gives a very interesting mass spectrum. And especially, I want to draw your attention to the product line 94. And it has been demonstrated that the 94 is actually a secondary fragmentation of the 392, which is created by the loss of ammonia from the M+H. And it's the loss of ammonia which actually induces two electron swaps from this position to there and from this position to there, leading to the formation of a morpholine ring, and the loss of this whole part, so ring opening, and the loss of this whole part of the molecule. And then you say, how do you know that this is involved and basically initiated by the loss of ammonia? That is, in order to do this, you have to have a certain minimum distance between the nitrogen and the carbon to create a ring. So if you would sterically hinder this fragmentation, that is, if you would rivetize the nitrogen by either putting a dimethyl on it or acetylate it, there will be sterical hindrance, so the carbon and the nitrogen cannot come close, and you don't see the 294 fragment ion anymore. Yeah, this indicates that in fragmentation you have far more factors playing a role. In some cases, also sterical factors in producing these things. And of course, we can explain all the other fragments in the fragmentation, but that's not important for the time being. We just, I just wanted to point it out, this 294 fragment ion, as I did. So this is the end of the first presentation, the second session of today. So we have our, unless there are questions, if not, we have our 10 minutes break, and we'll come back in a few minutes after 12 with you, and 11 for Sophia. And see you in 10 minutes.
See you soon.
Okay. So hope that the others are joining us as well. And we'll proceed in the second presentation of this morning. And in doing so, we'll start discussing about the fragmentation of amides. And you should be aware of the fact that the fragmentation of protonated amides is the best studied fragmentation for protonated molecules. And the reason for that is that the amide bond is also the peptide bond. And there's no single class of molecules where more people work on in mass spectrometry than peptides and proteins. You have huge laboratories where they run peptide and protein mass spectrometry 24/7. And so there's also, because of that, there's also a lot of interest in studying what is actually going on in particular cases. So what we actually see in the fragmentation is that the amide bond, so the peptide bond itself, is actually the weakest link in the molecule. So what we can see is we can have the cleavage of the bond with charge migration to the carbonyl function. So we have the acylamine or oxonimine and the loss of the amine. Or alternatively, we have charge retention, where we cut the same bond. We get a hydrogen rearrangement to the nitrogen. So we get a protonated amine, and we see the loss of ketene. And because of the stability of the acylamine and the high proton affinity of the amine, quite often you see both these fragment ions. And when you see both these fragment ions, the sum of their M/Z values is M/Z of M plus H plus 1. And here I have some examples. And if we look at the first example here at the bottom, we basically see 2 fragment ions, 147 and 89, adding up to 236, which is due to this cleavage in this particular case with charge retention either on that side or on the other side. And 2 additional fragments which are observed are due to losses of ammonia, perhaps or most likely leading to a 5-membered ring as indicated for the protonated 72 here, and probably the same holds for the 280. You also see this set of complementary ions in the spectrum of the amyloride, where we see the 171 and the 60 due to the cleavage in this particular case. And these 2 fragments are the major fragments in this particular case. And you see other fragments, and these are explained. So I promise you tables. So here's the table for the amides. You have the charge migration, the charge retention reaction. And if we have an aliphatic acylamine, you can always see losses of CO from that. Well, I said this is important in the fragmentation of peptides. So let's look at a simple example of that to get an idea of what is going on. And if you would have a singly charged peptide, you would expect that the protonation will take place on the amino terminal of the peptide. But according to the mobile protein hypothesis, this proton can move around along the backbone of the peptide to with the internal energy which you put in by the CRD, induce fragmentation. And basically what we say, if we would have the charge sitting here, we can have the cleavage of this bond, and that can lead to charge migration to get the acylamine, and what you will lose is the smaller peptide. And alternatively, you have hydrogen rearrangement to the nitrogen, cleavage of the bond, and protonation at the peptide, so you get the protonated peptide and the loss of the ketene. Yeah, and this is this way, and basically there's this 4-center mechanism which I introduced earlier for the amines would be here as well. However, it has been indicated that there are a number of alternative fragmentation mechanisms involved in the fragmentation of peptides. For instance, involving the nucleophilic attack of one of the carbonyls to the carbon of another carbonyl, resulting in the oxazolone derivative. And this oxazolone derivative will subsequently fragment between the nitrogen carbon bond and produce the two ions. And alternatively, another nucleophilic attack may occur where the terminal amino group attacks the carbon of the protonated amine bond to result in decatopiperazine derivatives. And all these type of mechanisms have been discussed, and there are even more specific things which have been sorted out and which found out in this peptide fragmentation. And if you would like to dig deeper in the type of mechanisms which have been described, I have indicated you two nice review papers to do so. But as I said, I want to not go into too much into all these mechanistic parts. So when we say this, and we have this mobile proton, in principle, we can have this amide cleavage, bond cleavage, at any amide bond in the peptide. So we can have a variety of product ions, and according to the nomenclature rules set about by Professor Peter Roopstorff in the 1970s, we will call all fragment ions containing the N-terminal, where the fragmentation occurs at the peptide bond, we call them B ions, and we number them from the N-terminal, and the complementary ions will be called Y ions. So we have a Y series and we have a B series. The M/Z difference between, for instance, the B2 and the B3 ion, or in this particular case, the Y2 and the Y3 ion, will be what we call the residue mass of this amino acid. And the residue mass of an amino acid is the mass of an amino acid minus water. Yeah, so you can set up a table based on the elemental composition of the various amino acids for the residue masses of the various, in this particular case, ribosomal or proteogenic amino acids. Yeah, so if you want to do interpretation of the MSMS spectrum of a peptide, you get Y ions and B ions, and basically you have to fit in amino acids between these ions. One of the problems which you immediately will face is that you don't know which ions are B ions and which are Y ions, which complicates the story a little bit. If you have a known peptide, so with a known sequence, you can actually predict the sequence ions which you can get, so the B ions and the Y ions. And the B ion, so the B1 ion, is the residue mass of the N-terminal amino acid plus 1 plus the H. The B2 is B1 plus the residue mass of the second amino acid, and so on. And if you have all the amino acid there, so you have the Bn, the M/Z value which you will get is the N plus H minus 18, because we still have 18 left here. For the Y ions, we work from the other side. So the Y1 fragment ion will be the C-terminal amino acid plus 17 plus the rearranged hydrogen plus the H plus. So the residue mass of this C-terminal amino acid plus 19. And you can proceed by adding residue masses of the next to get a complete series. And if you have done the complete series, the Yn will be the N plus H. So we can take a known sequence, which is indicated here. It's a triplet peptide. In this particular case, a short triplet peptides, and we can calculate the sequence ions. And then take the MSMS spectrum and see what we actually get. And we see the Y1, the Y2, the Y3, the Y4, and the N plus H, which is the Y5. And the B series is not complete because we don't see the B1, And basically, the formation of the oxazolone intermediate is one of the reasons to explain why you cannot see the B1 ion, because you basically get a ring between the N-terminal and the first amino acid from that side. So we see the B2, the B3, the B4, and the B5 being the 540, which is N plus H minus 80. And in this, we have a known sequence, so we can easily see, and we also see that there are some additional issues in the spectrum because the relative abundances between the various sequence ions can be substantially different. We can see additional fragmentation, due, for instance, in this particular case, due to water loss. We can say what we call an A ion, which basically is the B3 ion minus CO. So in the sequence, we will actually we cut here rather than at this position, and these things, so missing sequence ions, low abundant sequence ions, and so on, complicate the interpretation of the spectra. And nowadays we have bioinformatics tools which allows us to do this interpretation much faster and much easier than we normally have. So let's move to the small molecules. Let's move to amides again and have this type of fragmentation. And what I'm going to look at are three isomeric compounds, which I call the ortho, meta, and para, indicating the relative position of the N-acetyl group to the sulfonate substituent. Yeah, so I have an amine, an NH2, N-acetyl, and a sulfonate on the aromatic ring. And I have three compounds. And if I look at the MSMR spectrum of the ortho compound, I see what I would expect. That is, I will have the loss of the acetyl, so the loss of 42 to the 198. And according to the four-center mechanism which I introduced before, you would expect that you have hydrogen rearrangement from the carbon to the nitrogen, and then the cleavage of these two bonds, and you basically lose the ethanol, which is the CH2CO, like this. Yeah, so if this would be the underlying mechanism, you would expect to see exactly the same spectra for the meta compound and the para compound. Well, in fact, you don't. Because while you see the loss of 42 in the ortho compound, you see the loss of water for the meta and the para compound. So in order to come up with an explanation, we basically invoke the so-called ortho effect. And in an ortho effect, two neighboring groups on the aromatic ring can have influence and have interaction, and that may change the fragmentation. So in order to write a mechanism, what we do is, instead of having the hydrogen rearrangement to nitrogen, we actually do the hydrogen rearrangement to one of the oxygens of the sulfonate group. And then we have a whole range of double bond swaps, which ends up by the loss of the ethanol. And then this is what we have. And then basically the hydrogen moves back to the nitrogen again to get the 198. And from the 198, we can have the losses of the H2SO3 and the H2SO2 to the fragments 107 and 123, which are also shown in the spectrum. Yeah. If you would have the same ortho effect for the meta or the para compound, it is not the N-acetyl, but it's actually the NH2 group, which is now interacting with the sulfonate group, forming a ring by the loss of water. And from the ring, we can see losses of SO and SO2. explaining the 149 and the 165 product ions. And you can write this same mechanism for the para compounds, because only this is on a different position in the molecule. So groups next to each other, depending on their properties and so on, may influence the type of fragmentation you actually see. And this is what is called the ortho effect. Okay. In the table I showed you before on the amides, I also had carbamates. And carbamates also give a characteristic fragmentation, where basically the weak spot in the molecule is between the oxygen and the carbonyl. So what we see is we see hydrogen rearrangement to the oxygen and charge migration to the oxygen. So what we basically see is the protonated alcohol and the loss of the R3 and CO. And the characteristic loss which we frequently see because we have a lot of N-methyl carbamates is the loss of 57. Alternatively, we see the loss of the alcohol and we see charge retention. So basically what we get an ion like this. And these features have been observed in this MSMS spectrum of the carbofuran, because what we see from the carbofuran is the cleavage of the carbonyl oxygen bond leading to the base peak on the spectrum, which is the 165. And we also see the 58, where the charge resides at the other side of the molecule, which is the 57 plus H, of course. And this Italian group, at a certain stage, using a Q-TOF instruments, start to look into the grass of the molecule. And also, we can say something about 123, because the 123 must be secondary fragmentation of 165, involving the loss of propene. So we can propose this structure for the 123. And for the various peaks in the grass, they come up with elemental compositions, and they propose structures for these product ions. And I have no problem with most of their structure proposals, except for the 137, because the 137 can only be formed by having two CH2 losses from the 165, or perhaps in another way. Maybe, but I don't have any evidence for that. Something which you would have to investigate. You have in the fragmentation change from the 5-membered ring to a 6-membered ring, from which the loss of C2H4 is more likely to occur, but I don't know. I'm surprised by this structure proposal. I will never make it myself as such. Okay, let's take another carbamate. And again, I have an N-methyl carbamate, and what I'm looking at is I start interpreting. So I start from the 239 to the 195, which is a loss of 44. And from the tables I showed you before, most likely it will be the loss of CO2. But the CO2 loss should come from the middle of the molecule, and you have to rearrange a bulky group. And sometimes I say, oh, it's only a small peak. Let's ignore it. Let's move on. And then we go to the 182. And we see the loss of 57, which from our table, no, it's the characteristic methyl NCO. But in this particular case, then we have a problem, because we do not have a methyl NCO, but we have a dimethyl. So in order to explain the 57 here, we will have to rearrange the methyl group to the ring and then kick off the methyl NCO. So for both the 195 and the 182, we have to invoke skeletal rearrangements in order to explain the fragmentation. And if I have that, I would basically need to have accurate M/Z data to prove that that is what is going on. So what I do is basically say I have the elemental composition of my parent compound, and let's assume that we see the loss of CO, and this will be the elemental composition of the 195 fragment. And if you have the loss of the methyl NCO, this will be the elemental composition of the 182. So we can calculate the exact M over Z. We can measure the M over Z using accusative instruments, and from the small M over Z differences which you actually see between calculated and experimental, you can be pretty sure that these elemental compositions are actually correct. And of course, you check whether there are other elemental compositions possible for these, but they are not. So basically, we come to the conclusion that yes, what we actually have in the formation of the 195 is the loss of CO2. And I've proposed that the dimethyl N is going to this position of the ring. So the CO2 comes out from in between. And I also made a structure proposal for the 182. And of course, I cannot be sure about these structure proposals, but some certainty comes from the fact that from both these structure proposals, I can basically explain all the other fragments which are there in the spectrum. So that gives us some confidence that what we do is actually going well. This is another situation where we have a phenylurea compound. So we have a urea substitute with either in this particular case, a phenyl and dimethyl in this particular case. And what we actually see are cleavages on either side of the carbonyl in the urea in this particular case. So if you would cut at this side of the carbonyl, what we will get is by proton rearrangement and charge retention, we get a dimethylamine, which is the M over Z 46. And the other ion is the 188, which would be the acylium ion, because basically this is an amide fragmentation. And you see that the sum of these is 2, 3, 4 is M plus H plus 1. We also see the base peak, which is the 72, which basically is the dimethyl NCO. Yeah. And then I say, well, I would expect a complementary ion. So I would start searching for the 162. But the 162 is not observed. What you actually see is the 160. And we can write a structure proposal for the 160. And then we basically see that if we cleave at this side of the carbonyl, we get complementary ions. If we cleave at the other side of the carbonyl, we get a direct cleavage where the sum of the M over Z values equals to the M plus H plus 1, as we have seen other examples before. This is something typical what we see. I will just skip one page, and the last example I have for you today is on a skeletal rearrangement and how this was sorted out in a nice way. So we are looking at this particular compound, which is a farnesyl transferase inhibitor with a mass of 405. So we see 406 as the M plus H. And if I look at the spectrum, there are two features which strike my attention. And that is, I see the loss of 28, so the loss of CO, which basically can only come from this position in the molecule. And in addition, I get two fragments, which is the 81 and the 326, which can be complementary fragments adding up to 407. Okay. Then I say, let me have a look at the structure and let me try to predict where I will get fragmentation. And then I say I would expect to have cleavage of this nitrogen-carbon bond, cleavage of this carbon-carbon bond because of the imine, cleavage of this carbon-nitrogen bond, yeah. And each time when I would have a fragment which contained this ring, I can have an additional fragment involving the loss of CO from that. Yeah. So if I follow the lines indicated, I get 160, 289, CO loss 261. And in the same way, I get these other values. So basically from this, I have already predicted 10 of the fragment product ion, because I also have the CO loss from the M+H. And I can transfer this information to the spectrum and indicate, hey, I have explained these peaks. And quite a lot of the fragments are actually explained now, except the 326 and the 81. And from the fact that I see the loss of 28 from the 326, in the 326, I still must have this group. So what I'm now going to do is trying to sort out what is going on, what is the 326. And in order to do so, I will do what is sometimes called a pseudo mth to the power 3 experiment. So what I will do is I will not start working with an ion trap, because in the ion trap I will get a different fragmentation, especially because I will not be able to trap the ions at the low end of the spectrum. So what I actually do is I'm starting to use in-source CRD by increasing the voltage on the ion sampling RFIs, by which I can induce fragmentation of the compound in the source. And when we do so, we see that one of the fragments which we produce is a 326. So from the ions, product ions produced, or fragment ions produced in the source, I can now select the 326 and do MSMS on this 326, which hopefully helps me to get some idea about the identity of the 326. And what I see from the 326 in the MSMS spectrum is the loss of CO. And I see the 116. But I also see that all other fragments here are actually different from what I have in the spectrum of the intact molecule. So what I now need to do is try to find out what is going on. And one of the things I can do, and I must indicate I don't have accurate mass data, so I cannot simply do calculations of what I would like to do. So, but basically, I would like to do some calculation of possible elemental compositions for one of the fragment ions. And of course, I will take the smallest possible one, because then I get the least number of hits. Yeah, and I assumed that the 81 and the 326 are due to complementary fragments as they add up to 407. So what I do is I paste in the elemental composition of the parent compound and start performing elemental composition calculations. In this particular case, I use the software from Micromass von Waters, which is in the MassLink software. And then I get I use a wide tolerance window because I don't have accurate mass. It can be odd, it can be even electron ion, I don't know. So in this particular case, I only since it's the fact that I have complementary ions, it cannot be odd electron ion, it must be an even electron ion, sorry. And then I will check the various elemental compositions which come up and see if there would be an easy and logical way to actually explain such a loss from the structure which I have. And I don't succeed in many cases, but in this particular case, I get a C4H5N2 elemental composition, which would be consistent with the methyl imidazole, which is part of the structure of the molecule as shown here. So basically, I propose that the 81 is actually this product ion. And that means that I need to come up with a rearrangement reaction, which allows me to get rid of this 81 product ion. And this is something which I can achieve by performing a intramolecular SN2 reaction, in which I move the benzyl group from this nitrogen to the nitrogen of this ring. And then I can easily kick off the 406 and immediately write a structure proposal for the 326, like this. Yeah, so we see a massive skeletal rearrangement by the rearrangement of a benzyl group and kicking out the intermediate group between the benzyl group and the position where it goes to. And I remember in one of our previous sessions, somebody asked, how often do we see this skeletal rearrangements? Well, fortunately, we don't see them too often, but still, every now and then we see this. And quite often, this could involve rearrangement of a benzyl group. So you can, if you have that, you may have this possibility, and you may see this type of fragmentation. And I'm sure that you don't want to, do not like to see that too often in your compounds. And for instance, just imagine that you would you would have a drug where this skeletal rearrangement occurs, and you want to do a MET-ID study. The strategies which are outlined for doing the MET-ID study will not be that easy if you have this type of skeletal rearrangement. And I can assure you that this is actually true, because I once had a MET-ID study where we actually saw such a benzyl rearrangement, and sorting out the metabolites was pretty complicated. This brings me to the end of this presentation. Again, there are exercises for you to work on in between today and tomorrow morning, because tomorrow morning at 10 o'clock at your clock, we will reconvene and discuss the exercises which follow here. If there are no further questions, we will stop for today. And I say bye to all of you, and hope to see you all tomorrow. And perhaps even get a complete group. Okay, bye.
Bye.
Thank you.
Thank you, everybody.
Thank you.
Bye.
Bye.
Thank you. Bye.
Have a great day.